In this video, we're going to start chapter 10 on circles. So there's going to be a lot of vocabulary in this lesson because we're identifying the parts of a circle, making sure we know how to name them and notice them on a diagram, and then we're also going to use their properties. So be sure to pause the screen, get any of this written down, and then come back to fill in information because I am going to talk about how we actually name these different parts. Okay, so for a circle, okay, let me just, sorry, I needed to get that back to blue. All right, so for a circle is just the set of points that's equidistant from a fixed point. So in this case, the fixed point is A, and so this circle right here is equidistant. All these points right here are equidistant from this center or this fixed point. So A right there is called the fixed point. To name that, if you were going to name that point, it would just be point A, right? You know how to name a point from chapter 1, so it would just be point A with a capital letter. If we wanted to name the circle, we always name a circle based on its center, okay? So we would name this circle, we would name it circle A. So if you wanted to say it out loud, that's what it would be. If you see it with written down, it's going to have a circle with a dot in the middle and say A. So this would be circle A. And that tells you that A is the center point. Then a radius is a segment that connects the center point to anywhere on the outer edge of the circle, okay? So in this diagram, our radius is AC. It's a segment, okay? So remember, a segment would be named using its two endpoints, A and C, and then with a segment up top. You also could see that there's radii in here. So radii is the plural of radius. So you'd see other radii. So AD would be another one, AB. Okay, so anywhere that connects the center to the edge. Then we have a diameter. And now a diameter needs to connect 2 points on the edge, and it needs to pass through the center. So you'll see this diameter in blue goes from edge to edge, so point B and point D are on the edges of the circle, and this segment goes through the center point. So when we name this, again, we need to name using the endpoints, so B and D, and then with a segment above it. So BD is a diameter, it goes through A, we would name using the endpoints. So some more stuff in a circle. So we've got a chord. So a chord is similar to a diameter in the fact that a chord goes from edge to edge like a diameter. However, a chord does not have to go through the center. Okay, it could. If it goes through the center, it's a diameter. It doesn't have to. So a chord can just hit edge to edge. So ED right here is a chord. And again, name using the endpoints with a segment above it, so ED would be a chord. A secant, similar to a chord, except for that it's a line. So this purple line right here is a secant. Okay, it goes through the circle. It's a line that goes through the circle. So when you're naming a secant, we would use any 2 points on the line, and we would draw a line with arrows above it. So line GH is a secant. We actually have you could do a chord in there too if you just connected from G to H with a segment. So just G to H with a segment above it would be a chord. G to H with a line above it is a secant. So a secant has to be a line. Then we have a tangent. Okay, and tangent line is a line that touches exactly 1 point. Okay, so exactly 1 point, not more, not less. It's a line that touches right at that point, okay, 1 point on the circumference. And so when we name this line here, trying to figure out what color I had. Well, we'll just do this one. So when we name this line, you would name it using 2 points. This one doesn't have a second point, so let me add a second point on here. I'll just call I right there. Okay, so when we name this, we would go F, I, or IF, it doesn't matter, with a line above it. Okay, and then that point of tangency is where it touches. So point F, if you needed to label that, is the point of tangency. Okay, so a tangent line hits once, a secant line hits twice, a chord is a segment that goes edge to edge. Then we have the circumference. So circumference is just all the way around the circle, okay? The entire distance around the circle, all the way, okay? And it's a linear length, so measured in like feet, inches, yards, centimeters, that kind of thing, so the distance around it. An arc is just part of the circumference, okay? So just a little chunk of the circumference. So if you thought of this as a pizza or a pie, an arc would be just the crust, okay? So just a part of the crust. And then there's all sorts of different types of arcs, okay? So we've got, first let's talk about a central angle, and then let's get into the types of arcs. So for a central angle, and let me cover these up while we talk about them. So for a central angle has its vertex at the center, okay? So A is going to be the center of the central angles. So you'll see a couple different central angles here, okay? So you could look at this one as a central angle. So this would be angle DAB, okay? So the vertex is that center, and then two other points on either side. You could also do DAC would be another one. So if you went over here, if we did DAC, this would also be a central angle. Okay, but you name it using 3 letters with the vertex in the middle. Okay, so it's centered at the center. And then for arcs, okay, so we have a major arc. So remember that the total degree measure of a circle is 360 degrees. So a major arc, okay, major being big, a major arc is an arc that is more than halfway around or more than 180 degrees, okay? So you could do a major arc could be like this. Okay, there's some other ones in there. That's not the only one. But bigger than 180 degrees, so more than halfway. So when we name this, a big arc needs to use 3 letters. Okay, or 3 points. Okay, not 4, not 2, 3. Exactly 3. The first 2 of them have to be where it starts and stops, and then any other one. So I'm going to start at C, and then you can pick either B or E. So I'm going to do B, and then D. So C, B, D. So start, where are you going, and then where are you finishing, and then you put an arc above it. Okay, so this would be a major arc. So when you look at it, okay, you know that it's more than 180 degrees because of those 3 letters. A minor arc. So a minor arc is an arc less than 180. So minor being small, so less than halfway. Okay, so a couple of them here you could do. So I'm going to do this one. And for a minor arc, we always use 2. So not 3, even if there's another letter in here, not 3, just 2 letters, where you start and where you stop, and then an arc above it. So DB could be one. You could say BD as well. You could do CD or DC, CE, EC, EBBE. Okay, so any of those are fine. So notice that the angle goes into the circle and uses the vertex. The arc stays outside of the circle. So we're not talking about the vertex or any interior parts. We're staying on the edge. And then finally, a semicircle. So a semicircle is an arc with exactly 180 degrees. So it's halfway. So the starting point and the ending point are going to be a diameter. Okay, so in this case, so I'm just going to go this way. So I started at B, went through E, and ended at C. Again, 3 points for a semicircle. So if you see 3 letters for an arc, you know it's either 180 degrees or more. Okay, if you see only 2, then you know it's a small arc. So this will tell you which way to go. Instead of for B to D, so you know not to go this way. Because if it was a major arc like that, a big arc like that, it would have to have had 3 letters. All right, then let's take a look at the couple of properties that we're going to be working with for circles. So that's just the vocab to be able to name stuff, know what I'm talking about. So this first theorem tells us that in a plane, okay, a two-dimensional surface, if a line is tangent to a circle, okay, so you see this blue tangent line to the circle, meaning it hits at one point, okay, a line is perpendicular, or a line is tangent to the circle if and only if it's perpendicular to the radius. Okay, so you'll know if it's tangent, it's perpendicular to the radius. Or if you see a line perpendicular to the radius, it's automatically a tangent. So this has to happen. If you see this, tangent, radius, perpendicular, those three things always go together. Tangent, radius, perpendicular. Then if we see tangent segments, okay, so tangent segment just means it stops. They just didn't extend it. It could extend, right? So we could extend it and it would be a line, but they're just stopping. So they're starting out here at S, doing the tangent segment. Okay, so it's tangent here at R. That's a point of tangency. T is a point of tangency. If you see that, then these two tangent segments are the same length. Okay, so these two segments right here, RS, is congruent to TS. So they're the exact same length. If this is 10, this is 10. This is 5.2, this is 5.2. All right, so let's use those properties here. Okay, so let's take a look. Given that segment AB is a radius, okay, so they're telling you that this is a radius, determine if, okay, so determine if BC is tangent. Okay, that means we don't know yet, we need to find out. So if in fact it is a tangent, okay, so if this segment right here is tangent, and I like to highlight it, okay, so here's the potential tangent, here's the potential radius, okay. If this is a radius and a tangent, what would happen is this right here would be a right angle, okay, meaning this whole thing right here would be a right triangle. So how do we know if something is a right triangle? Well, it satisfies Pythagorean theorem. So we're going to plug those lengths in here and see if this is a right triangle. So remember, the tangent and the radius are the ones that might be perpendicular. So those are our legs. Okay, across from the potential right angle is the hypotenuse. So when you plug these in, this one is our C value. Okay, so 67 squared versus 60 squared and 25 squared. Okay, so we're trying to see if these are equal to each other. So 67 squared is 4,489. 60 squared is 3,600. And 25 squared is 625. So let's add those two together. So 3,600 plus 625 is 4,225. Okay, so those are not equal. So this is not a right triangle, meaning that this angle B, okay, so angle B is not equal to 90 degrees. So this is not a tangent. Okay, in order for BC to be tangent, it needs to be perpendicular to AB. Okay, so this means that BC is not tangent to circle A. Okay, so next one. So again, determine if AB, so AB is the radius, determine if BC is tangent. So this is the radius, and then we're trying to decide if this is tangent. Okay, so that would mean that those two are our legs, so this would be our right angle, and this would be our hypotenuse when we go to do Pythagorean theorem. Okay, so C squared. I'm just going to leave a circle here instead of putting an equal sign since we're trying to decide if they're equal. All right, so we know that 3 and 4 are the legs, so I'm going to put that in here, 3 squared plus 4 squared. And then we need to look at this hypotenuse. Now remember, the hypotenuse always has to be the longest side, and we see the 2 here. The 2 is just for this portion of it. Okay, remember that this part right here is a radius as well. So from center to edge, Remember, the radii in the circle are all the same. So this one is 3. So the total length here from A to C is 5. So that hypotenuse is 5. So then 5 squared is 25. See how that compares to 9 and 16. Okay, so 25 compared to 25. And we find out that those are equal. Okay, that means that it is a right triangle. So angle B does equal 90 degrees. So this is tangent. So BC is tangent to circle A. And then last two examples. So this one is similar to what we just did, okay, except for this one, when we're trying to decide, okay, so here's our radius and here's the potential tangent. So now when we go to do C squared equals A squared plus B squared, okay, I'm going to plug in the legs first. Okay, so this one is telling us that it's already tangent. So we already know that these are tangent. So we know that this statement is true. So I'm going to plug in the legs here. So I have x squared plus 24 squared because those are our legs, right? And then our hypotenuse is from here all the way out. So remember on this last one, when we had the 3 and the 2, we added those to get 5, the total length. So we're going to need to add these to get this total length. So the total length is x plus 18. And remember, those aren't like terms, so we would just write it down as x plus 18 squared. Okay, so this is going to require that you FOIL or do the box method to figure out simplifying that. Okay, so most of you, if you are here, probably use the box method. So you put x and 18 on top and on the side, multiply. X times x is x squared. X times 18 is 18x. X times 18 is 18x. And then 18 times 18 is 324. So then we would have like terms here when we take this out. Okay, so we'd have x squared plus 18 and 18x is 36x plus 324 equals x squared plus, and then 24 squared is 576. Okay, so then notice that you have an x squared on both sides, so I'm going to subtract x squared to get those together, and they're actually going to cancel out on both sides. So then I'm down to 36x plus 324 equals 576. So I'm going to get these like terms together, the 324 and the 576, by subtracting 324 from both sides. So 576 minus 324 is 252. And then divide both sides by 36. And you'll get that x equals 7. Okay, so if we go back up to the problem, okay, x equals 7 was our radius. Okay, so x equals 7. Then the final example uses the idea of the tangent segments. So if you remember what that said, it said that the tangent segments are equal. Okay, so then these are just equal to each other. So we'd have 3x plus 4 equals 28. So then you can solve by subtracting 4 from both sides. So 3x equals 24, divide by 3, and you get x equals 8.